Thank you, James. So today I'm going to be talking about cryptography, and the talk title is technically, helps if the button works. Buttons don't work. Who needs buttons? I'll just use that. Things every dev should know about cryptography, which I actually wanted the talk title to be things I wish I knew of cryptography when I was a dev, but didn't. I think I made some fundamental mistakes in, thankfully, a practice app that never went to production. I'm kind of hoping that no one else makes these types of mistakes. DevWorld 2025. That's kind of the plan of the talk. And so I am a cybersecurity instructor. I teach cybersecurity for a living. I have been for the last 5 or 6 years. Teach all sorts of stuff in cyber. I'm a recovering developer. I still develop on the weekends and stuff because you just can't take the developer out of you. You get stuck in there, you live there, you breathe it. Now, one of the things that was not mentioned in Tony's talk this morning is that there is a theme you'll see in some of these talks, which is it's really important for every talk giver to put an anvil or an anvil drop into every presentation. So I've managed to find one, rather using Google image sourcing, using AI art. It's so good. And so here is this year's one for me. There we go. It's lovely. It's great. It's wonderful. And then while asking for it, mine is like, no, it's an anvil. Shut up. Don't. It's a thing. Don't analyze the image. Now, my AI is starting to get a bit sassy with me because I asked for this, and then it goes, "Here's your ridiculous anvil masterpiece." What? That's not what it's getting sassy with me. This thing, and as much as I love it, maybe it's getting sick of me, and that's okay. We'll figure it out between us. We'll figure it out between us. Now, let's talk about cryptography, and I'm going to avoid maths, because maths sucks, even though it's entirely driven by maths. Now, I want to talk about what is encoding and encryption, because they get used interchangeably, but they do mean different things. I want to talk about hashing, which is also not encryption, but is still important in this topic. We're going to talk about how it gets used for passwords a little bit. We'll talk about symmetric and asymmetric encryption, which are sort of the two main bundles of encryption. And we'll also talk about how we use it, which is for encrypting, which is sort of a big part of it, but also for something called digital signatures and code signatures. You would have come across code signatures every time you have code signature problems putting things onto devices. And then I want to sort of talk about the last topic very briefly on quantum, which is spooky. It's a new thing. It's a thing that, 5 years ago, I was like, oh, this feels very science fiction, very far in the future. And now it feels like it's very close. It's very nearby. And so there are some ramifications in the world of development and security that we need to be aware of. And there's some really prominent aspects coming to iOS, Apple OS 26 that we need to be concerned with. Are people calling it Apple OS now? I'm going to try to make this happen because I don't want to say iMac, Watch, Pad, Vision, whatever next. Apple OS is what I'm calling it. Hopefully they'll figure this out. Now, when it comes to encoding and encryption, encoding is changing something from one format to another. Now, the best easy example of this is Morse code, where you're going from letters into dots and dashes or to long and short, depending on how you're doing it. Now, I don't think anyone in this room would say that Morse code is encryption. It's clearly not, right? You're just changing something from one format to another. Now, encryption is changing something from one format to another, but not all encryption, all encryption is encoding, but not all encoding is encryption. And that is something that there is that sort of disconnect. And probably the best example of this disconnect is base 64. Now, I can't see my screen here, and I know why now, because Apple doesn't like showing me multiple screens. But just to give you a quick view, and I know you can't see it, I'm going to bring it up in just a moment, because it's not on mirror, it's on... that's why my clicker's not working. And I like privacy or something. I think that's me, I don't like privacy by clicking that. Now, this is base 64. And we're going to see what I can do here. So if I type in hello world, and I go to encode it, and I make the screen bigger, hopefully, right? And I look at that and I go, oh, look, encryption, I can't read that, right? And that's what a lot of people think, right? I've seen Adobe do this in their documentation where it's like, oh, look, it's encrypted with base 64. It's not encryption. Encryption needs a key. There's clearly no key here. I can take this string, copy it, put it into any decoder on the planet. There you go, decode. I agree to my lack of privacy. Paste, decode, and I get back hello world, right? There was no key involved. Now, this is not even made for security. This thing's got padding in it. So I can like take this Q, change it to an R, so completely change the input a little bit, and then I'll still get the exact same hello world. Like there's no security in this thing. It's not made for it. Now, going back to my slides here, I'm going to go to the next one. Hashing, also not encryption. When we talk about encryption, we talk about encrypting and decrypting. We are encrypting from a plain text, something you can read, to ciphertext, something you should not be able to read. And then we can decrypt from that ciphertext back to the plain text. That's the whole point of encryption, decryption. Hashing is one way. We go from some bit of text or a file or a message, and we get to some hash, some representation. Maybe it's 128 bits worth of something. We can't go from 128 bits back to like 2 terabytes of information. If we could, we've solved world storage. Like that's lossless compression, chef's kiss, who needs Amazon anymore, right? But that's not how it works, it doesn't work like that. The other thing it's really important for is it's deterministic. The same input will always give me the same output every single time. And we need that because the whole point is if I've got this 4 gig file and someone makes a tiny change in that, I need to know that something has changed in that file. And we do that by comparing hashes. And if the hashes are different, then there's obviously be a change in the input because same input, same output, different input, different output. So it's heavily used for integrity checks. We use hashing all the time. It does get used for passwords. And I've had development teams where they have taken a password, hashed it, and stored the hash. And that's not a good practice. The reason for it is that if I have a whole bunch of different hashes, I'll do a quick example here. I don't like doing an extended display. I'm very confused now. Okay, MD5 calculator. This will do. Right, if I type in hello world, right, so I have this hash. If the tiniest change happens to this input, let's change that D to a P, and I generate it, instead of saying 5EB whatever, it'll come with 012, right? It's meant to detect tiny changes. Now, if everyone has the same password, which is hello worlds, then the hash stored in the database is always going to be this thing. It's always going to be the exact same hash. It's always going to be cannot connect to server. Had a Chris Pratt moment there. It's like, man, you may have no connection to the internet. But let me go backwards there. Oh, we're really stuffing up today. We're going to go back to the slides. So let me go back to here. So we have to use a better algorithm. So not just hashing. There's something known as bcrypt, scrypt, pbkdf2, or argon2id. These are designed to be slow. And a lot of developers are like, well, no, I want fast. These are slower because they're GPU resistant and they're harder to brute force. So there are good algorithms that you should be using that introduce some randomness to it and make it slower. So if you are going to be storing passwords, don't store hashes directly, use a good algorithm. Now, when we talk about hashing, I just showed you MD5 and that website said SHA-1 as well. These are no longer considered secure, even though SHA stands for Secure Hashing Algorithm, right? It used to be secure, but it's not anymore. And the biggest reason for that is collisions. And collisions is when you have 2 different inputs giving you the same hash. Now, we are talking about an infinite space going into a finite space. You have to have collisions at some point, but we don't want them to be computationally feasible. And for MD5, it can be done about 0.6, like 65 cents per collision. I think that's USD, so maybe like $1 in AUD, which again, pretty easy to generate. So if I give you a quick example of that, let me go terminal. Can we move this across? Yes, we can. Starting to feel like Bob the Builder. Let's see how many kids' TV show references I can get into this thing, huh? So I've got two different pictures here. I have a ship. It's a good ship, not a ship. No, I can't say that. It goes against code of conduct. And then we've got a plane. There you go, two totally different images. And if I drop, well, not drop, I need to MD5 sum, sorry, MD5 sum. And if I put, I don't know, the ship in there, drag it across, you'll notice I have a hash that says, it begins with 253D. And if I do the same thing with the ship, no, that was the ship, let's do the same thing with the plane. That would have been amazing if it was the same picture. That would definitely give it to us, right? I will get the exact same hash, right? This is bad. If someone was to create like a signature and say, oh, I did this thing and I signed it and I replaced that with something totally different, and you're like, yeah, that's the thing I signed. That's bad, right? So we don't like collisions. That's why we don't use MD5 or SHA-1. We use the SHA-2 family. We use the SHA-2 family. So let me click through this. So if you've heard of SHA-256, SHA-384, SHA-512, these are all part of the SHA-2 family. At some point, probably in my and your lifetime, we're going to go, oh, whoops, we broke SHA-2. Let's move to SHA-3. And then maybe we'll go to SHA-4, which doesn't exist yet, and then SHA-5, or whoever knows what comes next. We need this cryptographic agility because even in my lifetime and in yours, we've already deprecated certain algorithms or certain key sizes. So we have to make sure we are up to date with what's relevant right now, especially what's coming in the next few years as well. I'm going to talk more about some of the recommendations coming up soon. So let's get to encryption. Now, the thing that you're probably most familiar with is the concept called symmetric key encryption, which is that you're using the same key for encryption and decryption. And you probably got introduced to this in primary school with something known as the Caesar shift cipher. The Caesar shift cipher is when you take the alphabet and you shift it by like 3. So if you're going to write down an E, you write down an H, right? I had to work that out. And you know, you then get a ciphertext, and you look at that ciphertext, and it's weak to something we call frequency analysis. And frequency analysis is that we look at the ciphertext and go, geez, a lot of H's in this thing. What if I change those all to E's? There's a lot of D's in this thing. What if I change those all to A's? Oh, I can probably figure this out. And then it becomes a cool puzzle, right? So that is called frequency analysis, and it's the reason why a Caesar shift cipher is terrible, right? We obviously don't use it. We use algorithms these days. And the main ones we use is AES, which is the Advanced Encryption Standard. It's a nice thing that's going to age well, just like the secure hashing algorithm. But for now, it's pretty good. We're going to have a better one in the future, probably. Now, AES runs in lots of modes. GCM, Gallo counter mode, is the better one right now. It's the one we prefer. There are bad ones. There's ones known as ECB, which is Electronic Code Book, I think. When it comes to ECB, there's a well-known picture known as the ECB penguin. I love this thing. Has anyone seen this thing? ECB penguin? This is the ECB penguin. The idea of ECB is that, let me bring up a bigger picture of it. There you go. Is that with this mode, you have your text, you split up into blocks, and then you encrypt with the key, and you get an output. And then you encrypt this block with a key and an output, and this block with a key and an output. And it's all very sort of separated out. The problem is same input, same output, same key. If you have patterns in your data, like in a picture of tux, you will get very obvious patterns in your ciphertext. Now, all I'm telling you right now is use the good modes. I'm telling you this because Microsoft recently published an update with Outlook and it had bad modes in it as default, right? This is something we're still getting wrong in today's world, and that sucks. I don't like that. So GCM is a well-known good mode. There is another one called, I have to get to the bottom here because it won't let me do it, char20 poly 1305. Don't ask me who names these things. And And this is, you'll probably start to see both of these in TLS if you do a lot of website stuff. It's good, right? It works well. There's some caveats around it. It's a stream cipher, so you have to make sure you always have a unique IV and stuff, but we don't care about this course, or this talk, so just be aware of that. Now, it's meant to be faster, and if you're asking your AIs what should I use, it'll tell you that CHA-20 is faster in pure software, and it is, but Apple designs their hardware with AES acceleration. And so it is significantly faster. So here's a quick little playground run where I did 2 megabytes 50 times, AES-GCM significantly faster than CHA-20. So even though AI is going to tell you CHA-20 is faster, that's not necessarily true for Apple hardware. Stick with AES. It's good. We like it. Now, it's not perfect. It's amazing for being secure, for confidentiality. It's fast. We use it for what we call bulk encryption. Big things we encrypt with AES. It's great. But it's not great for other security requirements. Now, those new modes like GCM and CHA-20, they have something we call authenticated encryption with associated data. And all that is just a fancy way of saying we've got some integrity checks and some authenticity checks in it. So now we do confidentiality and integrity and authenticity. This is phenomenal. We like it. That's all I need to know there. Now, the biggest disadvantages is key distribution. So let's say I've got a really big file. It's the movie Wolverine. I love Hugh Jackman. He's such a cool guy. And I want to encrypt it and give it to Tom. I have to give him the movie, and I also have to give him the key. Now, if I you can't email Wolverine movie, but if I had to give it to him in some format and put the key right next to it, I mean, that would work. He could decrypt it. But anyone who has access to that container would also have the key. It's like putting the key in your front door, right? You don't do that. And so I need to do some sort of out-of-band mechanism. So maybe I WhatsApp in the key or some other mechanism, signal or whatever. Now, so key distribution is a challenge when it comes to symmetric. Oops. Scalability is a challenge. And if there is a key compromise, like someone steals the Wolverine key that I use for all my movies, then everything can become compromised with that one key. And if you want an example of where this has gone wrong, or I guess for our perspective goes right, is when the Germans were doing this with the Enigma machine. And Enigma machine is pretty cool. I've actually used one, actually. It's basically, this is one of the most this is one of the things that was used in World War II. But Alan Turing and his team figured out what the daily keys were. And once they figured that out, they were able to decrypt communication for that day. And they did that every day. It's very cool. Don't want to talk about it here, but symmetric encryption has a lot of advantages, but can have some disadvantages. Now, one of the things that's interesting to me is that in the latest version, we call the ASVS, AES 128, what we sort of know and love, is being set to legacy. A lot of things in life that I've used, like Objective-C, have become legacy now. There's some reasoning behind that. I still think you'll see it around for a little while. I still see as the main one in TLS, stuff like this, but it's interesting they've set it to legacy. And I can see why, and I'll explain why that is in just a moment. Hint, it's quantum. But that's what we're going to talk about there. Now, asymmetric. This is something we've been using for the last 50 years. This is really cool. I sort of understand it, but I also don't. It's known for mathematically related keys. And if you want to think public-private key, I'm fine with that. There's other ways of doing it, but for this talk, for our conversation, I want to do public-private key. That's fine. Now, there's some things to note with this. Some of the use cases. So we do use it for encryption. We also use it for digital signatures or code signatures, as you're probably familiar with them in Xcode. And we also use it for something called key exchange, so giving a key across a medium that we can't control, an untrusted medium. Now, there's a few things I want you to know. The first thing is that we finally have a system where the public key or the key can go to anyone. We don't care. Here, have my public key. It's yours. You can have one as well. Like, you can all have a public key, but the private key must remain private. If that is ever compromised, the whole system is blown out of the water. It doesn't work, right? The private key must remain private. If that is lost, stolen, or somehow worked out, it's catastrophic for the system. Don't use those keys anymore. Now, here's the thing that if I teach a lot of people in security, this is something they always give you in an exam, which is if you encrypt with one key, you must encrypt with its mathematical opposite key. So if you encrypt the private key, you must encrypt the public key. if you encrypt the public key, you must decrypt the private key. And it's the two mathematically linked keys. It's not some other key out somewhere on the internet. These are mathematically linked. It's not magic, it's math, which has some magic to it, but just stick with the maths on this. Now, there are two ways to make this work. So the first way is I'm going to send a confidential message. I'm going to send a confidential message to Phil. All right? And I want him to sell him a secret message that I'm going to send to his brother. He's got a brother called Ben I used to do teaching with. And in order to send him a secret message, I'm going to encrypt a message with his public key. So I've encrypted a message with his public key. Now, or should I say, what key is the only thing that can decrypt it if I've encrypted with Phil's public key? Someone tell me. His private key. And who has access to Phil's private key? Only Phil. That's so important, right? Because therefore only Phil can decrypt it. Therefore we've got confidentiality. That's perfect. That's half of this. If you understood that, we're doing well so far. Sam knows I'm going to pick on him next, because I was looking at the faces and I recognize Sam and a few others. So let's say I'm going to send a message to Sam, and I'm going to encrypt a message with my private key. So we've just learned they're going to be mathematically connected and all these things. So if I've encrypted something with my private key, what's the only thing can decrypt a message? My public key. Who has access to my public key? Everyone. So everyone can decrypt this message. That sounds really dumb, right? But we use it all the time. All the time, because it's not about confidentiality. If we want confidentiality, we've got it. I encrypt with the recipient's public key. This is about authenticity. You know this came from me, because only I could have encrypted it. Because only I had the private key. If someone else got it, we're all screwed, right? Only I could have encrypted it, therefore we know that. If you are familiar with digital signatures, if you're familiar with code signatures, that is what this is. It is encrypting a hash of the message of the software. It's a hash of that with the private key of the maker of that software. And therefore everyone can check to see, hey, is this valid? Because you've given them your public key. Hopefully this is sort of like fitting into place in these weird areas you've had over the last 10 years. It is at the core, that is all it is. There's no other use cases. Those are the two use cases. Let's try the other ones. I encrypt something with my own public key and only I can decrypt it. Asymmetric is slow as hell. You would never want to do that. Encrypt something with someone else's private key. You can't touch someone else's private key, right? Those use cases make no sense. Those are the only use cases that make sense. So hopefully that's made that more clear. Now, there's a picture of it where AI can't spell Alice twice. But yeah, so basically, we do that. Now, I already mentioned this one as well, which is developer perspective. Now, I said we give away public keys. You're like, Louis, I don't remember giving away a public key. Certificates are just a fancy wrapper for a public key with some identity stuff and some crypto stuff. Cryptography, not cryptocurrency. Sorry. And so here's AEC, right? There is the public key for the AEC website. That's what a certificate is. It's a fancy wrapper. Now, we trust AEC for lots of reasons, mostly because Tony's a great guy. But there is something known as a root certificate, and this root certificate is in my keychain, or in my certificate manager, or sometimes in a browser, right? There's, for whatever reason, we know the head of this thing, we know the root of trust, and therefore we trust everything about it. That's the reason why we trust certain things. Now, when you go to deploy an application onto a developer device, it doesn't trust you unless you put a certificate on it, right? Because it needs to know, hey, this is a trust certificate. We trust applications coming from it, rather than it being some malicious application. So asymmetric is fantastic, but it's really slow. It's so slow. And it's limited. So for example, RSA can only encrypt the size of its key minus 11 bytes. Now, a large key size for RSA is 4096-bit. It can only encrypt that minus 11 bytes, which is only, 501 bytes of data? That's not a lot. That's barely enough to cover a meal, a succulent chunk. I don't know what's going on that. But it's a very small amount of data. And so this is really good for a hash, hence digital signatures, or if I want to do some bulk encryption of the Wolverine movie, and I want to send that symmetric key to Phil using his public key. Therefore, he gets this symmetric key through a secure way, through asymmetric, and he does the bulk encryption or decryption with the key he received. It's a cool system. I love this thing. It's really fascinating. So we do key encapsulation. I'm not going to go into this now, but we do key encapsulation, which is really lovely. Now, there's one interesting thing. I get people asking, is this how the internet works? This whole public-private key stuff? And the answer is no. There's definitely a lot of stuff out there that relates to this, but your browser, when you visit google.com or aec.edu.au, you're not giving away a public key. You're not giving away a certificate every single time. We don't have certificates for each individual person yet. Maybe that'll come. So we need something else. And we have something known as Diffie-hellman. It gets called point-forward secrecy for other reasons. But the idea is that we have some exchange. The end result is that through maths, we get a symmetric key. And so what happens is you've got Alice and Bob, and you've got malicious Mallory in the middle. If Mars was here, I was going to say malicious Mars, but she's not here this week, so that's a shame. We've got malicious Mallory in the middle here. And Alice and Bob have some agreed upon numbers, or paint colors in this case. And Alice and Bob are going to choose secret colors. They'll combine these two together, or Alice will combine these two together, get this lovely orangey color. Bob is going to combine these two together and get this sort of blue color. They will swap the two, mix it with the secret, and through the power of maths, they will get the same answer. How am I going for time? Can I ask? A little bit of time. We're going to try a demo I've never tried before. I mean, I've tried it while demoing it myself. And then I seem to have quit out of it. No, I didn't. Here it is. We're going to see if this demo works. And if it does, I'm going to try this again at another conference. But I'm really hesitant. So I'm going to try on a safe audience, and that is you. You are my safe audience. Phil, give me your favorite number between 1 and 1,000. No pressure. 823. Perfect. So this is one of those secret numbers, right? 823.
What's your mother's maiden name?
Not a number. Not a number. Can't put it into this algorithm. It'll get a syntax error, and then I will freak out. So let's make that smaller there. Sam, your favorite number between 1 and 1,000? 337. You know, I was practicing this in my head and I was expecting all the internet funny numbers. Neither of you came with internet funny numbers. So thank you, I appreciate it. Exactly, that's exactly what I was expecting from one of you. But that didn't happen. Now, I'm going to try this. Again, this may fail. We're going to find out. So this is the first calculation, that first bit of paint coloring. And we're going to exchange if this worked. No, it's still building. This is from a previous test. Give it a second. I'm going to exchange a number across to Bob. The actual mathematical formula is g to the power of a mod p. So modulo. It's never going to be bigger than 23. This number we're about to share. Again, this is a toy algorithm. Don't actually do this. And hopefully that's building. Yeah, this is like an M1 Max machine. It's not that challenging. You can do it. Yeah, but it's faster in my demos. faster in my hotel room going, should I do this?
It's because it's putting a simulator in the background. Yeah, it's always what happens on first run.
There's not first run, but I appreciate you making this more palatable while we're waiting for a spinny wheel sort of thing. I know we're all familiar with spinny wheels, but I try to avoid them in presentations. And it's not really succeeding for me. Did I get the same number again then? I must have got the same number again. So we've got 11 there. I think it's, we're going to find out. So, oops. This is just me not pressing play button properly. There we go. And so I'm doing it over here. So exchange this number to Alice. So the number over here is 17. Thank you. I did see it there. And so what I can do here is I will pretend this is over the network. right? And Mallory will see this number, right? Mallory's going to see 17 and 11. She sees this stuff going through. You can do it. All right. So the number goes across. That one from Bob is going to be, we said it was 17. Can't see the cursor. Hoping this works here. 6, 17. Great. And then this one is 11. Assuming this works, the shared secret between the two of them should end up being the exact same number. So if I click this button here, the shared secret which will come out down here is 7. And the shared secret that comes out here, because Command R doesn't work, I don't want to use in playgrounds, the shared secret should be 7 here as well. We got there! Hey, this is like the lamest magic trick you've ever seen, by the way. That really wasn't worth the presentation for it, but I'm glad you got to see it. The idea there is they come to the same key, and they're going to use that key for a lot of things. Every website you visit will do this under the hood, and they'll do it, they call it a ephemeral session key. Basically, every session you do has this key they make and then throw it away. And they use this. It's a bit more complex than this one. They actually use something called elliptic curve Diffie-hellman, but the principle or the idea is the same. We call it period forward secrecy. We see this in TLS. We see this in latest wireless encryption. We see it in a bunch of other places as well, which is really good. Now, it gets called key exchange, but as you just saw, the key itself does not get exchanged. It's agreed upon. That's why I like to call it a key agreement algorithm. Now, let's get spooky. Quantum. I know. Now, if the questions at the end of this are going to be, hey, how does this in-depth of quantum work? Please don't, right? Let me show you where I'm up to in my learning journey for quantum. My learning journey for quantum is this book here. This is where I'm up to. This is the Quantum Computing for Babies book. It's actually a pretty good book, actually. It goes through, here's what binary is. And, what a byte is. At some point it gets to we got some problems coming up. Here's a problem. What's 3 times 2? Well, that's 6. Not cool. What factors go into 6? All right, that's 3 times 2. I just told you that. But what if it's a bigger number? This is literally RSA I'm teaching you right now. This is like the factors of prime numbers. This is literally what this is. Now, the idea is, the thing we're worried about is that quantum computers might be able to solve these hard challenges that classical computers have trouble with. Quantum computing for babies. See, now you're at the same level I am. This is fantastic. This is good. Now, when it comes to what of quantum, they're on their way, right? And Google published this about 6 months ago. Their quantum computer, Willow, performed a standard benchmark computation in under 5 minutes that would take one of today's fastest supercomputers 10 septillion, 10 to 25 years, a number that vastly exceeds the age of the universe. I don't know what that means. It just sounds big, right? It sounds like they're doing some pretty smart stuff over at Google, and there's some places in China, and there's actually a lab at UNSW that's got a whole bunch of these $500,000 machines. They're doing calculations on single atoms. It's cool. There's some cool stuff out there. So a lot of our current asymmetric encryptions are becoming deprecated, or they will. Not quite yet, but they're on their way. So our RSAs, ECC, Diffie-hellmans, we think that in our lifetime they might be replaced by something else. So quantum cryptography needs to solve the problems that quantum computers are causing. And we're seeing the introduction to that at the moment. So there is a suite called the CNSA 2.0 suite, where this is what's recommended. You want AES for 256 bits, so we're still okay with AES as long as it's 256. You've got something known as MLChem and MLDSA, basically kyber crystals and dilithium crystals, because the people at NIST are massive Star Wars and the Star Trek nerds. But one is for key encapsulation, one is for digital signatures, SHA-2, 384, 512, and some other stuff here. Again, I'm not going to go into this. But there are recommendations for a post-quantum world. Now, iMessage is getting this. We've now got some post-quantum cryptography that's being baked into it, and now we're getting it in Apple OS 26 inside of CryptoKit. So we now have a few post-quantum hybrid public key encryption for a combination of classical and quantum safe algorithms. So the 3 that I've implemented are X-Wing. I'm not kidding, this is what they're named. There are a whole bunch of nerds at NIST. ML-Chem, which is Kyber, and ML-DSA, which is lithium crystals, which is used for digital signatures. And again, we're seeing that in TLS 1.3 and Safari and stuff like this, but we are going to see it in CryptoKit as well. So this stuff is on its way. Yeah. See how ridiculously awesome is this picture? I love this. AI is great for meme pictures. I will still hire designers for stuff that's important, but for meme pictures, I love AI for that. So good. So good. All right. So I did mention there was a document called the ASVS, the Application Security Verification Standard. If you've come to my talks before, I rant about how good this thing is, and they just updated it this year. And in there, they've got a lot of really good guides for how to make applications secure. They've also got a mobile version, which is not as good, called the MASVS, but it still has some really high-level things of what you should be doing for a mobile app or for a standard application inside the ASVS. It has a whole section on cryptography that it didn't have before of like, hey, this is what you should be using for these use cases. I highly recommend the ASVS if you have questions about security, and really a lot of the resources from OWASP are quite good there as well. All right, so what did we learn? Hopefully this has simplified a lot of the complexity or some of the unknowns or the lot of foundations for cryptography, or you already knew it and you were just seeing what entertaining spin I could put on it. Hopefully that helped you on that one as well. Please use approved algorithms, use APIs, playing around with your own crypto primitives. There are ways to get this stuff wrong in ways that we've seen happen before. So please make sure you read the right documentation. Sometimes the AI will give you good stuff, sometimes it won't. I've seen both examples there. So again, if you are using Cursor or ChatGPT, please make sure you get some feedback, whether it be human or standards, that to see whether or not it's something you've done safely. There's some good resources out there, and threats are getting more clever. We're seeing more AI vulnerability scanners, and I don't just mean looking for AIs, I mean like the top bug hunters in bug bounty platforms are now AI. And being able to then exploit those vulnerabilities is going to be rapidly faster over the next 6 months to a year. It's not quite happening just yet. We're seeing some of the threat groups use this, but our threats are getting more clever. So I will need you and your AIs and co-pilots and whatever, I need them to be clever too. And that's it from me. Thank you.